Hello. This is going to be a lecture about the logic that undergirds how statistical analyses are done. One thing I want to stress before we get started is that this is not the only way to do it. I think this is probably the most dominant way that people, or most common way that people do statistical analyses, but there are other ways to think about this. So let's just jump into it. So I'm defining a statistical analysis as a framework for producing knowledge from quantitative information. And here's how I see the framework works. There are these 5 steps. The first is to formulate a question. The second is to design a study and collect data. The third is to choose a statistical model for the data. The fourth is to use the data to estimate and draw inferences about model parameters, and we'll say what we mean by that. And then the last step is to use all of these things that you've done in the first 4 steps to make a reasoned judgment about the answer to your question. And that judgment may be that you don't know, which is perfectly fine if that's the reasonable thing to say. Now, these 5 tasks are all related. Obviously, the 5th one depends on what happens in the first 4. But, for example, the statistical model that you choose is going to depend heavily on how you did the study, how you collected the data. And obviously, you want to design a study and collect data that gives you a chance of actually answering your question. In this course, we're going to focus mostly on number 3 and number 4. We'll get some practice doing number 5. We also spend a little bit of time talking about how studies are designed, but this isn't a full course in design of experiments. We have a course in the statistics department for that. If you're interested in that material, that would be a good one to take, because that's a very important part of doing a statistical analysis. Okay, so to kind of introduce what's going on, we're going to keep this example in mind throughout this lecture. And here's the example. The question is a beer bottling company actually filling their bottles up to 12 ounces? So the study we'll do is we go to the bottling line and take a sample of bottles from the line, measure the volume of beer from each bottle. Now, there's lots of things to think about when conducting a study like this. So in the office hour, what I'd like to discuss is what considerations do we need to make in this study. Often there are constraints to how many observations you can collect. There are specifics of the question that may not be fully fleshed out in this simple statement of the question. There may be specifics about how beer is bottled at this particular company that will affect how we do the study. So something to think about before our office hour is what things do we need to think about. So after we do the study, we'll get a data set. And the notation that I'm using for this is Y with a subscript. And the data are just labeled Y1 through YN. And these are volumes of beer from N bottles that were sampled from the bottling line. All right, so if we do this study and collect this data, first thing I wanted to discuss is what type of answer to our question can we hope to obtain from this study? Remember, the question is the brewery filling up their beer bottles to 12 ounces? And I'm going to contend that there's only certain types of answers that you can expect to get from this study. One of them would be that it is plausible that macro brewery ABC, which is our generic name for this brewery, fills their bottles to 12 ounces on average, or that it is not plausible that macro brewery ABC fills their bottles to 12 ounces on average. We're not going to be able to say that macro brewery ABC on average fills their bottles to 12.97345 ounces. The reason for that is because it's not going to be possible to sample every single bottle from the brewery. We have to collect a subsample of them. And one of the main things that statistics does is it allows you to use a sample to say something about the broader population. But the trade-off here is that we're not going to be able to make precise statements about the actual population average, but we can make statements about the plausibility of hypotheses. Now, a statement about the plausibility of a hypothesis given data is called a statistical inference. That's how I'm defining it for this course. And the sort of formal way of doing this is called statistical hypothesis testing. And this uses inductive logic and probability to turn these statements about plausibility into a formal process that involves probabilities and numbers and all that. So before we get into the details, what I want to do is just to give a high-level overview of how we make these decisions about plausibility of hypotheses or statements. So before the experiment, what we do is we pick a decision rule. So in this case, we're trying to say something about the plausibility of the statement that the brewery fills their beers up to 12 ounces on average. And so our decision rule here is I will say, I will deem the statement implausible if my sample average, so the average of the Y1 to Yn, is more than X ounces away from 12 ounces. So if you're looking at this picture here, what we're saying here is, here's 12 ounces on this number line, here's 12 minus X, and here's 12 plus X. If I take the sample average of my data and I get something over here, I'm going to say that the statement that the average volume is 12 ounces is implausible. Likewise, if I get something over here, I'm going to say it's implausible. But if I get something within this range, I'm going to say that 12 ounces is actually plausible value of the average for the population. Now, we haven't said in this decision rule what this X is. That's going to be kind of the part where you have to do some calculations to figure things out. And the way we do that is we use a statistical model to determine what X should be in order to guarantee that we don't make the wrong decision too often. So for example, if I made X really small and I only deemed it plausible if it was like right near 12 ounces, I could just by sample variability get something that's outside of that range. And even if the hypothesis was actually true, I could say it's implausible, and that would be the wrong decision. Likewise, if I made it too wide, I would be very rarely saying that the hypothesis is implausible. So we want to be careful about how we pick this X, and there's a formal process for doing that. So let's talk about statistical models. My definition for a statistical model is a family of probability distributions meant to represent assumptions about how the data were generated. So there's a few key words in this definition. One is that it's a family of probability distributions. What that means is I'm not saying specifically that it's this particular probability distribution. What I'm going to be saying is that it's, for example, it follows a normal distribution, but I'm not saying what the mean of that distribution is. That's what I mean by a family. It's normal, but we don't know what the mean is. The second part of this is that it's meant to represent assumptions about how the data were generated. So when we write down a statistical model, we are explicitly saying what we're assuming about our analysis. We're assuming that it's normal, for example. This is important because this is a way to make it explicitly clear what we're doing in the analysis. I think one of the most important things to remember about what a statistical model is and what it's doing is it's our opportunity when we're doing the analysis to decide what we want to assume to be true and what we want to learn from the data. So first question you might have is, why do we want to assume anything? Well, assumptions will kind of bias things. If you can imagine walking around in the world without ever making any assumptions about everything and requiring evidence for making any decision that you'd ever want to do, you would never get out your front door, much less out of your bed. So we have to make assumptions, and that's particularly important in statistical models. We can't just say we know nothing about of what the data generating process was like, because we'll never get anywhere. That being said, assumptions do have their consequences, and we have to be careful about them. But the point here is that we're being explicit about what they are. That's the important point. Okay, let's go back to this modeling example. Recall that we labeled the data lowercase y sub I. The way a statistical model is going to work is that we provide a model for yi in terms of what's called a random variable, capital YI. So one example of a random variable is yi is distributed as normal with mean b and variance sigma squared. So this is my notation for specifying a normal random variable. This tilde here, you can read this as, quote, is distributed as, end quote. And then this is our symbol. In this class, I'm going to use the mean variance parameterization. In some other cases, you might see it written as normal mean standard deviation, which is simply the square root of the variance. But I'll always write the variance here. Okay, so let's go back to our definition of statistical models, a family of probability distributions. So what I mean by that in this specific case is that I'm saying it's normal, but I'm not saying what its mean or its variance are. So if we go back to this second line, what we're assuming to be true is that the y's follow a normal distribution. And then what we'd like to learn from the data is the mean, b, and possibly also the variance as well. All right, so just a quick reminder, this is what a normal distribution looks like, at least the best I could draw it. There's the center of the distribution is b, and then the bulk of the distribution is between, say, b minus sigma or b minus 2 sigma and b plus sigma or b plus 2 sigma. Now, I use this term random variable, capital YI. The thing about random variables is that random variables have probability distributions, like this picture here. This is a density function, and are not specific numbers. So for example, we can say lowercase y7, which is our notation for the data, equals 12.3, but we would rarely say something like the random variable y7 equals 12.3. Now there are caveats to this, why you would make a statement like this. If you study conditional probability distributions, you sometimes do make statements like this. But when I write a random variable, what I want you to think about is that we're not saying what the number is, we're saying what its probability density is. So these are kind of two fundamentally different types of objects. This is data. This is something I can write on this piece of paper. It's something I could type into a computer or store in a file. But this is sort of a more diffuse thing. This is this thing has a probability distribution. It doesn't possess a specific number. Now the notation we'll use in this course, and I'll point out when we fail to do this, is that we're going to try to use lowercase letters for non-random quantities. So for example, we're using lowercase y for the data, which is a non-random quantity. It's just a number. And a lowercase b for this parameter describing the mean of the normal distribution. And then we'll use uppercase letters for random variables. For example, this random variable y sub 7. The next part about probability distributions, if you notice here, I've said what what its distribution is. But I haven't said anything about how y1 is related to y2, how our model for the first observation depends on the model for the second observation. And to fully specify a probability distribution, you have to say how these random variables are related. For now, we're going to keep it simple. We're just going to say that the random variables y1 up to yn are independent. What this means, well, there's a formal meaning in terms of probability distributions, but for our purpose, what this means is that if you have some knowledge about what the first observation is, this tells us nothing about what the rest of them are. Our notation for independence is the following. We can write it like this. This collection of random variables y1 to yn is distributed as, with the IND letters above it for independent, normal, mean b, variance sigma squared. So this is one way of saying explicitly that all of these n random variables are independent. Another way of doing it is just to say yi is independent, and then it's understood that this is sort of a generic random variable representing any of these, and that they're all independent of one another. One of the key purposes of specifying a statistical model, one of them is to be explicit about our assumptions, and another one is that it tells us what the sampling distribution for our estimator is. Okay, so we just said this on the last page, but I want to have it on the same page here. Our model for yi is yi are independent, normal, b, sigma squared. And then our goal of this analysis is to say something about what the parameter b is, which is our population average volume of beer in a bottle. One way of getting an estimate for this population average is to just take the sample average of the data. So our notation for that here is I'm going to use the parameter and put a hat on it to signify that this is an estimate of this parameter b. So b hat is not the same as b. It's an estimate of b. And it's equal to the sample average of the data. So you should recall this notation from the previous lecture. One of the fundamental questions we have is, we have our sample of data, and we get an estimate of this population parameter, but how close is that thing to b, which is the actual population mean of the distribution? And this is where the model helps us, and we can use what's called the sampling distribution of the estimate to figure out how close it might be, or at least figure out how close it might be under the assumptions of our statistical model. So I'm going to define uppercase b hat as the same exact formula. Let me get them both on the page here. It's the same exact formula as lowercase b hat, but what I've done is I've replaced the data, lowercase yi, with the model for the data, uppercase yi. So whereas this is a sample average of data, this is a sample average of random variables, which is kind of a weird thing to think about. But if you take a bunch of random quantities and take some function of them, the output, which is the thing on the left side, is going to be a random variable as well. Now I don't have it on the page here, but we'll call this thing lowercase b hat, this is an estimate. And this uppercase b hat, just to give it a different name because it really is a different type of mathematical object. This is called an estimator, E-S-T-I-M-A-T-O-R. Now, since this is a random variable, it's a function of random variables, it itself has a probability distribution. And if you do the math, it turns out that the probability distribution of this estimator, capital B hat, it's also normal. It has mean B. This is a typo. This should say B, not B0. And its variance is not sigma squared, but it's sigma squared over n, which is the total number of random variables in the sample. So what happens is the mean of the distribution is not changed. It's still B, but the variance shrinks by a factor of 1 over n. So if you look at this figure here, whereas this gray line was the probability distribution of an individual yi, the probability distribution of the estimator is going to have the same center, B, but it's going to be kind of shrunk in a little bit. So it's a tighter distribution around the true population average. And if you think about this, this is the whole point of sampling many observations. as we sample more and more, this distribution will get tighter and tighter as n gets larger around the thing. So what this means is that under our model assumptions, we always have to be clear that we're making an assumption here. This b hat, which is sort of, we could think of this as the realization of this random variable, it's unlikely to be more than 2 sigma over square root n away from b. So if this is the distribution, this model says that this thing, it's going to be close to b, and how close? It's going to be roughly within 2 standard deviations, so roughly 2 times the square root of this away from the true value. Now the interesting logical flip is that, of course we don't get to see b. So the way we write down the model is we specify the model and then we say how far is the estimate going to be away from that. It's like model first, then data. But what we get to see is we only get to see this b hat, and we want to know how far is b away from that, not how far is b hat away from b. But these are really the same thing. So the logical flip here is that we could take this statement and say that the true value of the parameter is unlikely to be more than 2 sigma over square root n away from the thing we get to see, which is our estimate of the parameter b hat. All right, so that's some background about how these sampling distributions work. And what I want to do now is put all this together into sort of a formal process for making decisions. Okay, so we get data. I'm labeling this y1 to yn. We choose a statistical model. The notation here, I'm saying that the ith observation, ith little yi, we're going to model it with capital Yi. And what I'm writing here is distributed as p theta. So what I mean by that is this is just some, I'm trying to be generic here, that this is just some arbitrary probability distribution. This could be normal, for example. Then we state a hypothesis. Our hypothesis, sometimes it's called a null hypothesis, and we use the symbol H0. Our hypothesis is the statement that this parameter in the probability distribution is equal to some specific value, theta naught. So I'm saying theta equals 12, for example. The next step is to specify a statistic. So I'm going to use the lowercase u for the statistic. This is just a function of the data. So for example, the sample average. And the next two things are the significance level alpha. This is going to be a probability between 0 and 1. We'll say what we mean after we say what the decision rule is. And the decision rule is we reject or fail to reject the hypothesis based on the value of the statistic. So we're going to get a statistic. The idea is that the statistic tells us something about this parameter. And then we're going to make a decision about whether we're going to fail to reject or fail to reject this hypothesis based on this rule that we write down. The interesting thing here is that this decision rule, this is constructed, so we're going to have to pick exactly what we mean by this, so that the probability of rejecting the hypothesis H0, when it is true, is equal to alpha. So this is where the significance comes in. And the idea is we want to pick alpha to be small because rejecting the hypothesis when it's true is a mistake. And we want to make mistakes not very often. So we're going to pick this alpha to be small, like 0.05 or 0.01. And we use the sampling distribution of the statistic, which comes from the statistical model, to determine exactly what this decision rule has to be so that this probability is equal to alpha. Now, if that's all a little bit too abstract, let's put this to work on this bottling example. So here we're going to collect 100 samples, Y1 up to Y100, where Yi is the volume of beer in the ith bottle. Our model is that the Yi's are independent with mean B, so this is our unknown parameter, and variance 0.1 squared. Now this is a little bit strange that I would tell you that I know what the variance is, but not the mean. In practice, we're not going to do this, but this makes the calculation easier for this simple example. The subject of the next lecture is going to be about the t-test, which is a way of doing all this without making an assumption about the variance. But for here, to keep it simple, we're going to just say the variance is 0.1 squared, or likewise, the standard deviation is 0.1. Our hypothesis is the statement that B is 12 ounces. Our statistic is the sample average. By the way, we'll sometimes just call this Y bar for the sample average. Our significance level, remember we want to make this a small number so that we're guaranteeing that we don't make mistakes too often. I'm going to pick 0.05. By the way, there's been lots of discussion about, this is kind of the default in a lot of sciences. There's lots of discussion about whether that should be the default, but we'll leave that. And then our decision rule is we're going to reject this hypothesis, B equals 12, if the difference between the statistic, which is the sample average, and 12 is bigger than some cutoff. So this is just another way of saying that we're going to reject the hypothesis if it's less than 12 minus C or bigger than 12 plus C. And then if it's between 12 minus C and 12 plus C, we're going to fail to reject. Now what's left is we have to use the sampling distribution of the statistic to determine what this cutoff is, where we should actually put this cutoff in order that the probability of rejecting a true null hypothesis is 0.05. And that's what we're going to do here. So just to remind you of what everything is and to give some specific numbers here. Suppose we take the sample average and we get this number, 11.93, which on this number line falls right there. So let's keep this to the side. This is our data. That's what that number is. Now the random variable version of the statistic, which is also known as the estimator, is you just take the same exact thing and you plug in capital Y's. And if you do the math to figure out what this distribution is, it's normal with the same mean, B, and its variance is 0.1 squared divided by n, which is 100 in this case. Now, we're not going to go through how you get these cutoffs, but I'm assuming that you've seen this before, that if you want to guarantee that the probability of making a, rejecting the null hypothesis that it's true is equal to 0.05, the cutoff that you should use is you take the number 1.96 and divide it by the standard deviation of the distribution. So there's a couple of mathematical steps here. The reason I get 100 here is not just because it's 100 in the denominator here. If you take the square root of this quantity, 0.1 squared divided by 100, you get 1 over 100. So I'll leave that to you to do that calculation. So that's why I'm doing 1.96 over 100 here. So this is our sampling distribution. This is this normal distribution with mean 12 and standard deviation square root of this, which is 1 over 100. And this is going to be our decision rule. So we have to pick this cutoff, and it turns out to be 12 plus 1.96 over 100, so that the area under the curve within this region is 0.95, which means that the area outside of that central region is 0.05, which means 0.025 on this side and 0.025 on this side. So this is a typo. This should be 0.025 and 0.025. So to put all this together, if our null hypothesis is true, it has this sampling distribution. We're picking this cutoff so that the area outside of this region is 0.05. So in this particular case, when we got 11.93, this is way outside this region. And so the result of our test is we reject the hypothesis that b equals 12. What we're really saying there, in sort of more plain English, is that we're saying that the hypothesis b equals 12 is implausible given the data that we observed under the model assumptions that we made. So if we're living in the universe where the null hypothesis is true and our modeling assumptions are true, this bump here is sort of the range of values of the sample average that you can expect to get. So if everything that we're assuming is true, you should get something over here. We got something way over here, which should make you question whether that hypothesis is actually true. This data is inconsistent with this hypothesis. And so the result is we're saying that this hypothesis is not plausible. On the other hand, if we had a different data set and we got 11.995, we would be here, and the result of our test would be to say that the hypothesis is plausible, or we fail to reject the hypothesis. So what statistical testing does is it allows you to make specific statements, specific hypotheses, and gives you an answer of whether that hypothesis is plausible or not. Now that answers the question that we had for this particular study. Is this brewery filling their bottles up to 12 ounces? But in other cases, you may not have such a specific question in mind. What you really want is to say, okay, here's our sample average. What are the sort of plausible values of the true population mean given that we've observed this particular sample average? And that's what a confidence interval does. So what I want you to think about here is forget for a minute about the exact precise mathematical definition of a confidence interval and think of it this way. The confidence interval is the answer to the question, which hypotheses are plausible given the data? What a confidence interval gives us is it gives us a range of plausible values of the parameter. And here's how it works. Actually, this is just one way that works, but I think this is the easiest to understand. So the way it works is we set up a hypothesis test for some specific hypothesis. And so everything works, the way we just laid out for null hypothesis significance testing. And we do the test. We say, is this hypothesis theta not plausible or not given the data? If it is plausible given the data, it goes inside the confidence interval. If it's not plausible, it is not inside the confidence interval. And then we repeat this for a bunch of different values of the parameter, and the confidence interval is precisely the collection of all values of the parameter for which we fail to reject the hypothesis that the parameter is equal to that specific value. So one way to think about a confidence interval, it's just the result of a bunch of hypothesis tests, and you collect the values of the parameter for which you fail to reject the hypothesis. So in a picture, it's going to look like this. So we got 11.93 for our sample average. And above, we did this hypothesis, b equals 12.0. We got a rejection. And so the result is that this value, 12.00, is outside of the confidence interval. So it's over here. It's not in this green region, which is our confidence interval. Then we do it again. We say, let's do 11.92. And I'm not showing the details, but if you picked this hypothesis, you would fail to reject it, given the data that we have. And so this one would be inside the confidence interval. So 11.92 is inside. If we did it again for 11.96, I'm not showing the details, but we would reject. And so this is outside the confidence interval. So you can think of a confidence interval. It's the result of doing a whole bunch of little tests, and then collecting the values of the parameter for which we failed to reject. And that would be specifically these values here. All right, one additional interesting fact about confidence intervals. And you can really think of this is really the definition of what a confidence interval is. But let's go through this. So we define B sub t to be the true value of the parameter. And we define capital Ci to be a random version of this confidence interval. Remember that a confidence interval is going to be sort of a specific set of numbers. These are numbers, these are non-random quantities. But you can imagine doing this whole process, but instead of plugging in actual data, you would plug in the random variable version of the data, and you can make probability statements about whether the true value of the parameter is inside the confidence interval. Another way to think about this is if you repeat the experiment many, many times and count the proportion of times that the true value of the parameter is inside the confidence interval. So we want to know what this probability is. And so this statement, the true value is inside the confidence interval, is equivalent to the statement that you fail to reject this hypothesis, because this is precisely how we define the confidence interval. It's the values of the parameter for which we fail to reject the hypothesis. Now, if just some simple probability calculus is that the probability of an event is equal to 1 minus the probability of the event not occurring. So this event not occurring means that you're rejecting this hypothesis. And we set up this hypothesis test so that this probability that you reject the null hypothesis when it's true, is equal to alpha. So the probability that this thing is inside the random version of the confidence interval is equal to 1 minus alpha. And this is why we call it so if alpha is 0.05, this is why we would call it a 95% confidence interval. So the formal definition of a confidence interval, it goes something like, it's the realization of a random interval that had 95% chance of including the true value of the parameter. So this is sort of the math for how you connect that definition to how we define a confidence interval, which is just the values of the parameter for which you fail to reject the hypothesis. And these two definitions are actually equivalent. So if you got a little bit lost in all of this math and logic about the confidence interval, that's okay. I mean, I do want you to sort of try to understand all the logic behind it. But the thing to come back to and to always remember is that the confidence interval is just a range of plausible values of the parameter given the data that we observed and the model that we assumed. So if you think confidence interval, think plausible values of the parameter. I think that'll get you most of the way there. All right. Final concept I want to go over is something called the p-value. P-value is another thing that's been controversial, but and there's good reasons for it being controversial, but I think you can't really criticize it until you understand exactly what it is. So often when we do this decision rule for a hypothesis test, it'll look something like this, that we reject the null hypothesis if the statistic is bigger than some cutoff value. Another way of saying is that it's more extreme than this cutoff value. So we can restate the hypothesis that we did before as we'll define the statistic itself as the difference, absolute difference between the sample average and 12. So this is a little bit different from how we defined the statistic before, but it turns out that it's you get a sort of an equivalent test. And then the decision rule works like this. We're going to reject the null hypothesis if this absolute difference is bigger than this cutoff. What the p-value gives you is it's the probability under the null hypothesis of getting a statistic as extreme or more extreme than the one we actually observed. So as a probability statement, the p-value is the probability that the random version of the statistic is bigger than the one we actually observed, which is u, which is the realized value of the statistic under the null hypothesis. So if we continue this in our example, Here is our statistic, difference between the sample average and the hypothesized mean. In this example, our sample average was 11.93, so our statistic is 0.07. Our rule is to reject the hypothesis if that statistic was bigger than 0.0196. This is what we have to pick in order that the probability of rejecting a true null hypothesis is 0.05. The random version of this statistic is just you plug in the random variable version, which is capital Y bar, sample average of the random variables. Remember that this thing has this probability distribution. And then we can go ahead and calculate the probability, the p-value, the probability that the random version is bigger than the one we actually observed. So this is probability that u is bigger than 0.07. That's our little u. The big U is this thing. So if you think about this, probability that this thing minus 12 absolute value is bigger than 0.07, this means that the capital Y bar is less than 11.93 or it's bigger than 12.07. So if you're out here, the difference between this and 12 is bigger than 0.07. Likewise, if you're out here, the difference between this and 12 is bigger than 0.07. So it's this statement. These are disjoint events. It can't be both less than 11.93 and bigger than 12.07. So by the rules of probability, we simply add those probabilities together. And then we can use R to calculate exactly what these probabilities are, and this is the R code for doing it. And I get 2.56 times 10 to the minus 12, which is like 0.000 with 11 or 12 zeros, and then 256. This is a really small number. And so the way we interpret this, we got a really small p-value, which means the probability of getting something as small as we did under the null hypothesis is a really small number. It's really unlikely. So our interpretation here is that the statistic we observed is very unlikely under the assumptions of the null hypothesis. Therefore, we deem the null hypothesis to be implausible. So if something really unlikely occurs, according to your assumptions, a reasonable thing to do is to question those assumptions. Now, it's true that unlikely things occur sometimes, but it's also true that sometimes your assumptions are wrong. And so it's certainly reasonable to question your assumptions if you observe something that is very unlikely under those assumptions. Now, there is a connection between p-values and testing, and you've probably seen this before, is that if the p-value is less than the significance level, so we got p-value equals this tiny number, which is less than 0.05, then we reject the null hypothesis. And if the p-value is greater than the significance level, then we fail to reject. So one of the sort of annoying things about doing this hypothesis testing is to figure out what this cutoff has to be. And so annoying I sort of skipped it in this lecture. But the cool thing about p-values is it allows you to avoid trying to figure out what that cutoff is. All we have to do is compute the p-value, and then we check whether it's less than 0.05 or not. All right, so that's our review of first course in statistics. Obviously, you do a lot more in a first course, but this is hopefully gets us onto the same page, gives us some examples of the notation that we'll be using for the rest of the course, and some things to think about and get your brain working again for the new semester.